In this section, we're going to consider another spatial image processing operation. It goes by the rather confronting title of mathematical morphology. Now, the word morphology means shape. So this is a type of spatial image processing operation that is sensitive to shape. The output image contains shapes that are compatible with a structuring element S. Now, the structuring element is a pattern which represents a subset of pixels within the input window that we wish to consider. An example will make that clear. We have a contrived example here, simple binary scene, black pixels and white pixels, that contains squares and rectangles of different sizes. As in previous animations, we see the input window, shown here in red, marching across the image left to right and top to bottom. What's different in this case is that the output is only true if all of the pixels underneath the red window are true. So far none have been. In a moment we will see that there's one particular case now where the output image contains a 1 pixel. That's where all of the pixels underneath the red marching window were all set. You'll notice that most of the shapes that were in the input image have disappeared. The rectangles have all disappeared, the little square has disappeared. The only shape that was retained was the big square. Note that the big square was the same shape as the red marching window. We say that only shapes that are compatible with the structuring element, a 3x3 square, are retained. This operation is also referred to as erosion, because what's happened is that our 3x3 square, even though it's compatible, has been eroded away. Pixels have been chewed off its edges until only the center pixel is left. This operation is often called erosion. And this function can be computed using the toolbox function iErode. The first argument is the image, and the second argument is the structuring element. In this case, it is a 3x3 matrix containing ones. So we can perform the converse operation, which is called dilation, and again we show this in animation. Here is the 3x3 marching window. But now for dilation, the output is true if any pixel underneath the red square is true. So far none have been, but now we'll see that there are a bunch of pixels are going to be set as the red window marches across them and encounters a 1 pixel. So this operation is called dilation for the obvious reason that it's taken a single pixel, dilated it, grown it into a 3x3 shape. In fact, it's back to the shape that it was originally. This function, this dilation function, can be computed using toolbox function iDilate. The first argument is the input image, and the second argument is the structuring element. So this was the original image that we had, and we eroded it to a single pixel. And then we dilated it so that the single pixel became a block of 3x3 pixels. So you can see what's happened here. We've taken an original image, we've eroded it and dilated it. And the only shape that made it all the way through was the 3x3 square. The rectangles have disappeared and the little square has disappeared. And that's because only the shapes that are compatible with the structuring element have been maintained. Now, this operation, this sequence of erosion followed by dilation, is often called opening. Only the compatible shapes have remained, and we can do this in the toolbox using the function iOpen. Let's try doing things in the opposite order. Let's dilate first and then erode. So in the dilation step, we can animate this, and for dilation, output pixels are true if any pixel underneath the marching window is true. And as we would expect for dilation, the shape is going to get bigger. But another interesting benefit of this dilation step is that holes within the shape are going to be filled in. So it's got bigger and holes within it have been closed up. Now we have a dilated image, and now we can erode it. So erosion is going to chew off a strip of 1 pixels all the way around the outside of this particular object. It's going to restore it to something like its original size and shape. Now let's look at the original image and then its dilated version and then its eroded version And we can see we have something that looks very much like the original shape, except the hole within it has been filled in. So this operation is called a closing operation. It tends to close holes within an object. So any hole that's smaller than the size of the structuring element, which is a 3 by 3 pixel block, will be filled in. This closing operation can be computed using the toolbox function iClose. So this brings us to the notion of compatibility between a structuring element and a shape. So here a structuring element is a red square, and I'm going to test it against a large square and a thin rectangle. So first of all, we're going to test the large square. And basically I'm saying that if I can fit the structuring element within that shape, it will survive in an erosion operation or an opening operation. But for the tall, thin rectangle, there's nowhere within that shape that the structuring element will fit. So this shape will not survive. It will be eliminated in the erosion step. Conversely, if my structuring element is a tall, thin rectangle, we'll find that there's actually nowhere that this tall, thin rectangle can fit inside the large square. So if my structuring element is a tall, thin rectangle, this square will disappear. However, the tall, thin rectangle will survive. So the shape of the structuring element controls the shapes that will be retained in the output image. It is a filter that's sensitive to shape.